1. Writing and balancing chemical equations. By the end of this section, you will be able to derive chemical equation from narrative, description of chemical reactions, write and balance chemical equation in molecular, total ionic, and net ionic format. The preceding chapter introduces the use of elements symbols to represent individual atoms. When atoms gain or lose electrons to yield ion or combine with other ions to form molecules, their symbols are modified or combined to generate chemical formulas that appropriately represent these species, extending this symbolism to represent both the identity and relative quantity of substances undergoing the chemical or physical change involves writing and balancing the chemical equation. Consider, as an example, the reaction between one methane molecule, CH4, and two diatomic oxygen molecules, O2, to produce one carbon dioxide molecules, CO2, and two water molecules, H2O. The chemical equation representing this process is provided in the upper half of the link, with the space filling molecular over models shown in the lower half of the feature. Reactant coefficient, product coefficient. The reaction between methane and oxygen to yield carbon dioxide and water, shown at bottom, may be represented by the chemical equation using formulas. This example illustrates the fundamental aspect of any chemical equation. A. The substances undergoing reactions are called reactant, and their formulas are represented and placed on the left side of the equation. B. The substances generated by the reactions are called products, and their formulas are placed on the right side of the equation. C. Plus signs separate individuals' reactant and product formulas, and an arrow separate the reactant and product left and right side of the equation. D. The relative numbers of reactant and product process are represented by coefficient numbers placed immediately to the left of each formulas. A coefficient of 1 is typically omitted. It is common practice to use the smallest possible whole number coefficient in the chemical equation, as is done in this example. Realize, however, that these coefficients represent the relative numbers of reactant and product, and therefore they may be correctly interpreted as ratios. Methane and oxygen react to yield carbon dioxide and water in the 1:1 ratio. This ratio is satisfied if the numbers of these molecules are respectively 1:1 or 2:4 or 3:6 and so on. Likewise, these coefficients may be interpreted with regard to any amount number unit, and so this equation may be correctly read in many ways, including one methane molecules and two oxygen molecules react to yield one carbon dioxide molecules and two water molecules. 1 dozen methane molecules and 2 dozen oxygen molecules react, yield 1 dozen carbon dioxide molecules and 2 dozen water molecules. 1 mole of methane molecules and 2 moles of oxygen molecules react to yield 1 mole of carbon dioxide molecules and 2 moles of water molecules. Regardless of the absolute numbers of molecules involved, the ratios between the numbers of the molecules of each species that react The reactant and molecules of each species that form the product are the same and are given by the chemical reaction equation. (4.1) Writing and balancing chemical equation. Balancing equation. The chemical equation described in section 4.1 is balanced, meaning that equal numbers of atoms for each element involved in the reaction and represented on the reactant and product side. This is a requirement. The equation must satisfy to the consistent with the law of conservation of matter. It may be confirmed by simply summing the number of atoms on either side of the arrow and comparing these sums to ensure they are equal. Note that the number of atoms for the given elements is calculated by multiplying the coefficient of any molecule's formula containing that elements by the element subscript the molecules. Formula. If an element appear in more than one formulas on the given side of the equation, the number of atoms represented in each must be computed and then added together. For example, both product species in the example, react CO2 and H2O, contain the element oxygen, and so the number of oxygen atoms on the product side of the equation is. The equation for the reaction between the methane and the oxygen to yield carbon dioxide and water is confirmed to be balanced per this approach, as shown in here. CH4 plus 2 O2, CO2 plus 2 H2O. Elements reactant product balanced. A balanced chemical equation often may be derived from the qualitative description of some chemical reaction by a fairly simple approach known as balance by effect. Consider, as an example, the decomposition of water to yield molecular hydrogen and oxygen. This process is represented qualitatively by an unbalanced chemical equation. Comparing the number of H and O atoms on either side of this equation confirms it's imbalanced. Elements reactant product balanced. The number of H atoms on the reactant and product side of the equation are equal, but the number of O atoms are not. To achieve a balance, the coefficient of the equation may be changed as needed. Keep in mind, of course, that the formula subscript define, in part, the identity of the substance, and so these cannot be changed without altering the qualitative meaning of the equation. For example, the changing of the reactant formulas from H2O and H2O2 would yield balance in the number of the atom, but doing so also changes the reactant identity. It's now hydrogen peroxide and not water. And O atoms balance may be achieved by the changing of the coefficient for H2O to O. H balance is unset by this change, but it is easily re-established by changing the coefficient for H2 product. This coefficient yields equal numbers of both H and O atoms on the reactant and product sides, and the balance equation is therefore 2H2O, 2H2 plus O2. Balanced chemical equation. Writing a balanced equation for the reaction, of molecular nitrogen N2 and oxygen O2 to form dinitrogen peroxide. Solution. First, write the unbalanced equation. N2 plus O2 arrow N2O 5. It is sometimes convenient to use fraction instead of integrals as the intermediate coefficient in the process of balanced chemical equation. When balance is achieved, all the equation's coefficients may then be multiplied by a whole numbers to convert fractional coefficient to integrals without upsetting the atom balance. For example, consider the reaction of the atoms ethane C2H6 with the oxygen to yield H2O and CO2, represented by the unbalanced equation C2H6 plus O2, H2O plus CO2, unbalanced. Following the unusual inspect approach, one might first balance C and H atoms by changing the coefficient for the two product species as shown in. This results in 7 O atoms on the product side of the equation, and at odd number, no integral coefficient can used with O2 reactor to yield an odd number. So the fraction coefficient 7/2 is used instead of the provisional balanced equation. The conventional balanced equation with integral only coefficient is derived by the multiplying each coefficient by 2. Finally, with regard to the balanced equation, record that convention dictated use of the smallest whole number coefficient, although the equation for the reaction between molecular nitrogen and molecules hydrogen to produce ammonia is indeed balanced. The coefficients are not the smallest possible, the integrals representing the relative numbers of reactant and product molecules. Dividing each coefficient by the greatest common factor 3 gives the preferred equation N2 plus 3 H2 2 and H3. The additional information in chemical equation. The physical state of reactant and product in chemical equation very often are indicated with a parenthetical abbreviation following the formulas. Common abbreviations include S for solid, L for liquid, G for gases, and AQ for substances dissolved in water, aqueous solution, as introduced in the preceding chapter. These notations are illustrated in the example, the equation here. This equation represents the reactions take place when the sodium metals placed in the water. The solid sodium reacts with the liquid water to produce the molecular hydrogen gas and ionic compounds sodium hydroxide, a solid in pure form but readily dissolved in the water. Special conditions necessary for the reactions are sometimes designated by the writing word or symbol above, below the equation arrow. For example, the reaction carried by heating may be indicated by the uppercase Greek letter delta over the arrow. CHCl3 heating, CHCO solid, CO2 gas. Other examples of this special condition will be encountered in more depth in the later chapter. Equation for the ionic reaction. Given the abundance of the water on Earth, it stands to reason that the great may the chemical reactions take place in the aqueous media. When ions and involves in these reactions, the chemical equations may be written with the various numbers and the levels of detail appropriate their intended use. To illustrate this, consider the reaction between ionic compounds taking place in an aqueous solution. When aqueous solution of CaCl2 and AgNO3 are mixed, the reaction takes place to produce the aqueous CaNO3 and solid HCl.